Pranav, just one question.
Yeah.
You saw the question I asked on WhatsApp, right?
Yes, yes. So
Is
I'll
that
think
true?
about it. No, no. So I don't understand. I mean, if you said two things commute and they're positive definite, then I mean, if you're only talking about those two things in life, then you can treat them as probability distributions. But yeah,
Yeah, that's all. That's all I wanted. I mean, is that like
yeah. But I mean, I thought that was fairly obvious. I thought you had something else in mind. I mean,
no, no, no. I'm
uh,
I'm verifying everything from
okay.
scratch.
Yeah, but you have to go to a common eigenbasis. Okay. So,
Yeah, so that's the.
uh,
I mean, my
I,
my actual question
I
is.
mean, that may not be the basis in which the matrices are originally presented.
Yeah, yeah.
So,
So that's the question. I mean, that's the question that they may rho a b sigma a b whatever they commute, and yeah, you have to go to a common eigenbasis. But my question is, can I write them down as a two cross two two cross two stochastic matrices like we usually write two probability distributions? Can we do that? That's
not 2 cross 2, n cross n.
n cross n, like a cross b
A
density.
cross B. No, 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 not A cross. I mean, the eigenbasis in general will be entangled states. The
Okay,
common
okay,
eigenbasis.
okay. We can discuss this after the class, I think.
Yeah. So I think, I mean, few lectures down the line, I mean, even Hari can join these discussions. So,
Yes,
yeah,
yeah.
I mean, yeah, I'll start with whatever, all these matrices basically. So let's start. Yeah, okay. So, this is what we're starting off. We are starting off with quantum probability information. What's happening? Information theory. Okay, good. Okay, so it's best to start off with some example. Okay. So let us say we start off with maybe the simplest probabilistic system classically. So that will be a bit. Okay, so we will talk of, let us say, the sample space. Let's call it X, which is 0, 0, 1. Okay, and then we can think of a probability distribution very simple, P 1 minus. And we will say the probability distribution. So far I was using P, but now I'll use the similar looking Greek symbol rho because that's more common in the quantum language. This P 1 minus. Now, the way I've written the probability distribution as a row vector. Okay. So what's the probability distribution? It's a vector. That means it's a tuple of non-negative numbers which add up to 1. So as like this famous probability theorist and statistician K.R. Partner, who was at ISI Delhi for a long time, and yeah, died. And before that, I think in ISI Kolkata also. So he has a very nice way of like describing the transition from classical probability to quantum probability. So we'll write down this is on classical probability. So whatever you have been doing in the probability course in the first year and in the subsequent years, advanced probability, it's all classical probability. So by classical probability, I mean that you start off with a sample space and then I start off with a probability measure on the sample space, so on. Okay. In quantum probability, my basic starting object is not a sample space. Let's see what it is. Okay. But to make the transition, what I'll do, what Parthasarathi says von Neumann did. So von Neumann, who first formalized quantum probability, was a function analyst. He loved matrices and operators. So as Parthasarathi jokes, instead of writing vectors as row vectors or column vectors, he started writing it as diagonal matrices. So I'm going to write the same probability distribution as a 2 by 2 diagonal matrix. Okay. Something looks like this. And as long as I'm only doing classical probability theory, I mean, there's nothing I have gained by this. I've just like earlier I used to write vectors as row or column vectors. Now I'm writing them as diagonal matrices. If I want to add vectors, I can add them coordinate wise, the same way I add matrices. If I want to scale a probability vector by 2 to the I max or something, as we do, like, okay, then I can scale the corresponding diagonal matrix by 2 to the I max. If I want to say one vector is coordinate wise less than or equal to another vector, I can also do it at the matrix level. Okay, so the corresponding diagonal entries are lesser in the first matrix as compared to the second matrix. So nothing seems to be gained. Okay, so this is all classical probability, but we will henceforth prefer to do classical probability using diagonal matrix. And for quantum probability, so Pascal like draws this line from classical to quantum. So the same object X, the basic sample space X, I will now say what it is. This is the two-dimensional vector space over the complex field. Okay. So what is that? Very simply speaking, the elements of the vector space are pairs of complex numbers, A comma B. So A is a complex number, B is a complex number. So the sample space was of size 2. It was a finite space of size 2. Classically, the quantum analog will be a finite dimensional space. So of course, I mean, the vector space C2 has infinitely many vectors, but the dimension is 2. So the size of the sample space translates into the dimension of the corresponding vector space. Okay? So the technical term for this vector space in the, if you look at quantum jargon, is Hilbert space, but for us, we just call it vector space. So Hilbert space is a vector space with an inner product. And the inner product over C2 we know very well, right? So let me write it down for the record. Like
It's also this separability, completeness, all those things are there.
Yeah, that is happens if you go to infinite dimensional vector space. We'll work with finite dimensional vector space, just as we were working with finite sample size. So let's see. So normally, if I have to write down a vector, I'll write it as a column tuple. Okay. So let us say I want to define the dot product of the vector this dot CD. So in the complex world, this dot product is defined by, okay. So you take the conjugate transpose of the first vector. So the transpose make the row vector into column vector, and then I do coordinate wise conjugation. Okay. And I just write this. And I multiply this as I multiply matrices. So this is a 1 cross 2 matrix. This is a 2 cross 1 matrix. The result is a 1 cross 1 matrix, which is A bar C plus B bar B. So this is the definition of the dot product. So you can see that A dot B, the vector AB dot CD is a certain complex number. Okay? So the dot product, also known as the inner product, is a complex number. Now, if I reverse the order of vectors, I do CD dot AB, I'll not get this number, but rather I'll get its complex conjugate. Because if I do CD dot AB, then out here it will be AC bar plus BD bar, the complex conjugate. So this is one notable property of the complex dot product, which differs from the real dot product. Okay. Of course, the real dot product is a special case of the complex dot product. And the reason we take this definition, which I'm sure I've already seen, is because we want the dot product of a vector with itself to be a real number greater than or equal to 0. And in fact, the dot product of a complex vector with itself is 0 if and only if the vector is the all zeros vector, or else it's a real number which is strictly positive. And then there is the other property of the dot product. So there is a distributive property. The dot symbol distributes over addition of vectors. Then there is the whatever the conjugate symmetry property. Like if I flip the two vectors, the result of the dot product becomes the complex conjugate. Okay, and yeah, so the conjugate symmetry, and then yeah, so and the positivity property that if I do A dot B, sorry, A B, A comma B dot A comma B, this is greater than or equal to 0. It's a real number greater than or equal to 0, and it's equal to 0 if and only if it's all 0. So I'm sure you're familiar with this dot product things. So let's proceed. So I mean, this was just to remind you that we will be looking at vector space as a dot product, and that's what the term Hilbert space means. Anyway, so now the probability distribution. So our basic objects of study are in classical were sample spaces, finite sample space, and probability distributions, which I'm now writing it as diagonal matrices. In the quantum analog will be finite dimensional Hilbert spaces. And what is the analog of probability distributions? So they are called quantum states, okay, also called density matrices. So what will this be? So this will also be a 2 cross 2 matrix, but it will no longer be a diagonal matrix. So that is the difference. So it's a 2 cross 2 matrix. And remember, the classical probability at the end of the day should be a special case of the quantum probability. So we will see that this diagonal matrix is a valid example of a quantum state, but in general, quantum states will have off diagonal terms. So now this is called quantum state. Also known as density matrix, another jargon. Okay. And this is the what it corresponds to. And this is what it corresponds to. This is what it corresponds to. Okay. And now I will tell you what types of matrices are allowed to be quantum states. So for probability distributions, I know what kinds of vectors I allow. So these are vectors with positive entries which add up to 1. So for quantum states, I will allow what are called Hermitian positive semi-definite matrices with trace 1. Okay. So let's understand this mouthful. Okay. So rho X is a 2 by 2 matrix. It's a Hermitian positive semi-definite matrix with trace 1. So these are matrices that can have complex entries. Okay, but I'm not going to allow arbitrary 2 by 2 complex matrices to be quantum states. So they have to satisfy additional properties. So one is Hermitian. Okay. So you have done linear algebra, right? As part of your mathematical structures.
Yes.
Yeah. Okay. So this symbol is very common in the quantum world. So this is just another term for rho conjugate transpose. This dagger is a symbol for conjugate transpose. Rho conjugate is you do the entry-wise complex conjugation, and then you take the transpose of the matrix. Okay. So now you will recall that the definition of Hermitian was rho conjugate transpose is equal to rho. So this is Hermitian.
No, I have a question.
Yeah. Then positive semi-definite means that so I will use this sign greater than or equal to 0 to mean positive semi-definite. So there are various ways of formalizing it. So we will discuss all of them. But for now, let us say that the formalization is eigenvalues are non-negative. So if people say positive definite or strictly positive definite, then that means that eigenvalues are strictly positive. The word semi-definite means that the eigenvalues are non-negative. Zero eigenvalues are allowed. And trace, trace is the sum of the diagonal entries, which is also equal to the sum of the eigenvalues. So trace rho equal to 1. So these are the three conditions: Hermitian, rho dagger, that is rho conjugate transpose is equal to rho. Positive semi-definite means that the eigenvalues are non-negative, and trace one means the sum of the eigenvalues is 1. So you can immediately see some connection to classical probability theory. So the eigenvalues look like probabilities because they are non-negative and they sum up to 1. Okay. So now you can immediately see that if I have a diagonal matrix, so rho equal to P1 minus P. Okay. This is Hermitian for sure. Okay. It is positive semi-definite because its eigenvalues are just the diagonal elements, P and 1 minus P, they're positive, and they sum up to 1. Okay. So this is a quantum state. So because of von Neumann strict, okay, the probability vector written in diagonal form becomes a quantum state. But of course, you can see that there can be more general quantum states where you have complex entries, you have off-diagonal entries. So you just have to satisfy this requirement. Okay. Hermitian, positive semi-definite, and trace one. Yeah. So now pause, questions, comments, doubts. Yeah.
Yeah, two questions. So first thing, none of the diagonal entries. So I just proved this, but none of the diagonal entries of a POS positive semi-definite matrix can be negative or complex, right? They have to be non-negative.
Correct.
All the diagonal entries have to be non-negative, right?
Actually, all the diagonal entries have to be non-negative and they have to sum up to 1 because trace is also
they have to sum up to 1. But such a constraint, I mean, this proof is easy to see. You can like suppose the ith entry is say negative or complex, whatever. Okay, then what I'm going to do is I'm going to take the vector which is 1 at I. Okay, 1 at I. And
so I'll be doing all that.
Okay. Sorry. And okay.
So as I said, there are various ways to define positive semi-definite. I chose one which is the quickest to write here and show the analogy with classical. But then we look at other ways, and you have to know the other ways also. Okay.
But there are no such other constraints on the off-diagonal entry. Off-diagonal can be negative, complex, anything, right?
Yeah. Off-diagonal can be negative, complex. Yeah. So I mean, a priori, I mean, when I've written positive definite, I've not said anything more, but the positive definite already implies that the diagonal entries have to be positive, and trace one means the diagonal entries have to add up to 1. So alternatively, you can say that, fine, a quantum state is this positive semi-definite matrix as we've just defined. Now to connect to classical probability, let me just look at the diagonal entries. They're positive and add up to 1, so I can think of them as classical probability. Okay, but like with more experience, you'll see that that's not the right way to embed classical probability into quantum. The right way to embed it is through the eigenvalues. Okay, so the diagonal entries of a density matrix are not necessarily the eigenvalues. Of course, I mean, in this case, the diagonal entries are the eigenvalues, but in general, the diagonal entries will not be the eigenvalues. Okay, so we have two candidates for probability vectors. I mean, if you want to find a probability vector hidden inside a quantum state, we have two candidates. One is the diagonal entries, the other is the eigenvalues. Okay, but for the correct analogy to classical probability, you should take the eigenvalues definition.
No, even that is strictly not true, right? I mean, there is a third way, which I don't want to say it now, but essentially measurement. I mean, the measurement you choose that gives you the distribution.
That's wrong, because measurement is losing information. Measurement will lose some of the entries of the matrix. Okay, so I don't want to change the matrix.
Okay.
So there were two candidates. So like it's only, I mean, after understanding more the theory, you realize which candidate is the right one to take. Okay, so at this point, of course, it's not clear. It's not even clear that the diagonal entries are positive and add up to 1. By the Hari, have you seen these things?
Yes.
Maybe you have already seen some of this. What a positive semi-definite matrix.
Yeah.
You did positive semi-definite matrix in your course?
Yes. Yes.
Okay, good. So then we can go a little faster. Okay, so let me write down some other properties of positive semi-definite matrix, equivalent characterization, which will be useful. Okay. So one characterization which is very useful is so let me write down positive semi-definite. So as I said, so one was like Hermitian. So okay, and eigenvalues. Positive or whatever, non-negative.
Non-negative.
Yeah.
Hey, come with me.
Just a second.
Hello? Shit, is my thing frozen? Hello? Shit.
Hello. Yeah.
Oh no. Oh, okay. I thought my screen was frozen.
Hmm. Good. Okay. So the other equivalent characterization is, so take a vector v, okay, and look at the dot product. So, let's begin. So the matrix is n. So v dot mv, this is a complex dot product. So this is greater than or equal to 0 for all v. So if it's a n by n matrix, so for all v in Cn. Okay. So often we use maybe a little clearer notation. So v mv. Another way of writing the dot product. This is an equivalent characterization. There's a third characterization which I mean is less useful, but you may have read it. So it says that all the principal determinants are non-negative. When I say non-negative, means they're real and non-negative. Okay. So these are all equivalent.
So principal determinant is what you take a sub matrix and take the determinant of that, or do you multiply it
So,
with the sign or something?
No. I'll explain this. So, but let's look at the second one. The second one is very important, occurs all the time. So v dot m. Okay. So let us say to prove the equivalence, at least we'll see the equivalence of 1 and 2. Okay. So to prove the equivalence, we take the Hermitian non-negative eigenvalues definition. Okay, to be the definition of positive definite. Now we so note that. So first of all, another useful thing which will be useful later on, very soon, which I don't know if you've seen, is the singular value decomposition. Have you seen this, Hari?
Yes.
Yeah, singular value decomposition. Good. You are well prepared. So any matrix so take any matrix M, which is a n times n matrix. We're only looking at square matrices right now. Okay. AI. UI, dagger. So dagger, remember, is a conjugate transpose. So AI is a column vector. Okay. And BI is a column vector, but once you take the dagger, it becomes a row vector. So this is a column vector multiplied by row vector. So it's a n by n matrix. So I'm writing the n by n matrix. I'm writing the n by n matrix n as a sum of n by n matrices, but they're of a special type. Okay, like this AI times BI dagger, and then these matrices are multiplied by some real number. In fact, non-negative real numbers, which are called the singular values. So let me write down the properties. Such that SI is greater than or equal to 0. Okay. Then the set of vectors AI, okay, is an orthonormal basis. So orthonormal means each AI has unit length. Unit length means its dot product with itself is 1. Okay, so that's the normal part, and AI dot AI prime is 0 if I is not equal to I. So that's the orthogonal part. So is an orthonormal basis of CN, and similarly BI is an orthonormal basis of CN. Okay. So this is the full power that any matrix can be written in this form. It can be written as a sum of n terms. Note that each term, okay, so AI times BI dagger, this is n by n matrix, but this is a rank 1 n by n matrix. Okay, so a general n by n matrix can be written as a sum of n rank 1 matrices. Okay, and the rank 1 matrix has special form. The rank 1 matrix is of the form AI times BI dagger, and the set of AIs forms an orthonormal basis. Set of BIs forms an orthonormal basis. But between the A's and the B's, there are no relations. Okay, this is, and then you have to scale this term AI times BI dagger by a positive real number, which I'll call SI. So the SIs are called the singular values. Okay, so now, so this is true for any matrix. Okay, I'm not saying Hermitian or anything. Any general n by n matrix can be written like this. So now, if M is Hermitian, so M equal to M dagger. Okay. So what does this translate to? So this translates to, so this is M. Okay. So I have to take SI dagger, but I mean that's a real number, so the dagger is itself. And now I'm taking the dagger, the conjugate transpose is, so I'll get BI AI dagger. And because of these orthonormality properties, so I mean there is a kind of uniqueness of the singular value decomposition. Okay. I mean, if stated correctly. So basically what this implies here, I mean, without going into a detailed rigorous proof, is that AI equal to BI for all. So in other words, if M is a Hermitian matrix, the singular value decomposition, okay. So what have I just proved? If M is Hermitian, its singular value decomposition SVD becomes like so. So this vectors AI are now the eigenvectors of M, okay, and SI are the eigenvalues of M. So this automatically tells me, okay, so I should be a little careful out here. So yeah, I mean, I did a fast one. So you can always have a scale factor, which you can, I mean, not fully absorb. So
So,
up to a sign, plus
can
or
I
minus.
can I sort of make a comment? So how would this proof? So you'll say that, okay. So let's take AIBI dagger.
Yeah, so-
That is a rank 1 matrix. So that is also also has to be equal to some other rank 1 matrix on the other side, but that might be some index J. So SI AIBI dagger would be equal to some SJ BJ AJ dagger. Is that the right way to go? Or
Okay.
not sure.
So for example, if all the singular values are different, then you can then you actually have a uniqueness. That if all the singular values are different, then this decomposition is absolutely unique. Okay. So if I'm writing N in two ways, okay, but then like I mean, I have S1 out here and I have S1 out here. That means whatever is multiplying S1 here has to be the same as whatever is multiplying S1 here. Okay. So that basically forces that AI is plus or minus BI. Okay, so I forgotten it at that moment. So there's a plus minus thing, because all I can say is that AI BI dagger is BI AI dagger. So that only fixes it up to this plus minus sign.
Okay, I see the proof.
In either case, it's
I see the proof.
and yeah, so it becomes more difficult when the SIs are not all distinct. Okay, then you have to do a little more detailed analysis. And I mean, essentially, you are breaking up the space into a bunch of subspaces corresponding to distinct SIs. Okay, and you have to argue separately for each space.
But Pranav, you don't need
But-
that, right? I mean, on both sides, you can say that act each matrix on BI. Okay. So because of LHS, you will only have SIAI, okay? Because of orthonormality of the BIs. RHS, you will have summation SJ, BJ, AI dagger, AJ dagger, BI. Okay. So,
Yeah.
so what you have is this whole expression in terms of BI, right? Right.
So
But
there are cross terms there.
there are
So
cross
you
terms
need
there.
you need something. Yeah.
Right.
So anyway, so let's So I don't want to give a rigorous proof, but I just want to correct singular value decomposition to Hermitian, and so give you a broader picture. So and singular value decomposition will be useful in several other instances also. So it's good to revise. So if M is Hermitian, so actually, I mean, this was a non-trivial theorem. If M is Hermitian, then it has an eigenbasis. I mean, its eigenvectors form a orthogonal basis, and its eigenvalues are real. So this is a non-trivial theorem. This is, I mean, part of the spectral theorem for Hermitian matrices. Okay. So, but here we have seen sort of a heuristic proof of this. That start off with the singular value decomposition. Let's say we assume the singular value decomposition, apply the M equal to M dagger criterion, and then we will see that the singular vectors. So the A's are called left singular vectors, the B's are called right singular vectors. But we'll see that the left and right singular vectors are the same up to this plus minus sign. Okay, so you cannot think of them as eigenvalues, but then you have to move the plus minus sign accordingly into the singular value. So what you will get out here is that these are the eigenvectors. They are orthogonal now because we know that the A's are orthogonal, and the eigenvalues can be positive or negative, okay, but still they are here. So that is a Hermitian matrix. So any doubts about this part? So
This also.
I'm just proved.
This.
Yeah, I've just proved that from SVD how you can infer that a Hermitian matrix has an orthonormal basis of eigenvectors with real eigenvalues. Yeah, somebody was asking a question.
This orthogonality of these
Just louder, please.
orthogonality of these vectors is only because of its Hermitian property, right? If it is not Hermitian, then it is not.
Okay, so singular vectors are always, the left singular vectors are always orthogonal. Right singular vectors are always orthogonal. Between the left and right, there is no relation. That's the general theorem. Okay. But what the Hermitian property gives, it forces a relation. And let us say, I mean, it gives a perfect matching between the singular values, which rigorously, for example, happens if all the singular values are distinct. Okay. So, but if they're not all distinct, then you'll have to basically group them into bunches. Okay. So let us say S1 is equal to S2, and then S3, S4, S5 are all the same. So there'll be one bunch for S1, S2, there'll be one bunch for S3, S4, S5. Okay. And then you have to argue separately in each bunch. I mean, it can be done, but I mean, if you do all that, then essentially you can equate them term by term. At the moment you equate them term by term, this says that AI is equal to plus minus BI.
Yeah.
Okay. For some I, AI is equal to BI. What I mean is, for some I, AI equal to BI. For some I prime, AI equal to minus BI. Okay.
Yes.
And then I get the expression. So for the first set of I, the eigenvalues are positive. For the second set of I, the eigenvalues become negative. Okay.
Okay.
So from the so basically SVD is the mother of this decomposition. And from SVD, you can infer that that a Hermitian matrix has this eigenbasis with real eigenvalues. So further queries? Okay. So now let's proceed. Okay. So I mean, the reason I was doing SVD is because I want to prove the second criteria. So now let me look at this expression. V inner product M. Okay. Now this is V inner product. Remember, for M we had the singular value decomposition. Right? Sum over I. So this should be greater than or equal to 0. Okay. For all V and P. So now what do I have? So this should be greatly equal to for all V. So let's say take V equal to B1, let's say BI. So then what do I have? The right hand side. Okay. So V is equal to BI. So BI dagger BI, which has a dot product of BI with itself, which is 1, orthonormal. And if I take BI prime dagger BI, that's a dot product of BI prime with BI, but orthogonality, that is 0. So the right hand side becomes BI, then SI, AI. So again, by the property inner product, this is SI BI AI. So this has to be greater than or equal to 0. Oh, so yeah, so this is okay. Sorry, minute, so not this. So what I wanted to say, yeah. So I want to suppose M is Hermitian. Okay, for now. Then so this is AI dagger, and
You're
and
proving
this I'll write it.
Hermitian implies this rather than this implies Hermitian.
Yeah. But I'll end up proving both very soon. Okay. So yeah, take V equal to AI. So what I have is AI lambda AI. Okay. So this is lambda, and this shows that lambda is bigger than or equal to 0. So suppose M is Hermitian, okay, with positive eigenvalues, then at least if I take V to be equal to AI, then inner product between V and MV is greater than or equal to 0. Okay. And now if I take a general V, so general
There
V,
is not Hermitian. I mean, assumption should be suppose M is positive.
yeah. So I'll come to the other side.
No. I'm
General
saying
V.
even on this side, you haven't assumed that lambda i's are positive. You've just assumed lambda.
No,
that-
yeah. So okay, let us say I'm proving the direction that M Hermitian with positive eigenvalues implies the inner product between V and MV is greater than or equal to 0. Okay.
But Hermitian
So
with positive eigenvalues is just means that the matrix is positive.
that, yeah, so that is our definition of positive definite. We want to prove the equivalence of the characterization. No. So
Okay.
the second characterization was this inner product of V with MV is greater than or equal to 0 for any V. Okay, so I'm just trying to prove that. So a general V, I can write it as a okay, some complex linear combination of AIs, right? You know, the AIs form an orthogonal basis. So alpha is a complex number. So then what do I have? So then V MV is summation I. So right. So yeah. So let me write alpha I AI, and this is MV. So this is summation I lambda I AI dagger, and this is summation I alpha I AI. Yeah, so I could have written this directly. But
No, wait. You cannot write M like this because
M is Hermitian, right? So I can write. So
no.
this
Which
is, that's why I wrote
direction?
lambda.
Which direction are you proving?
1 implies 2.
1 implies 2. Oh,
Let me
okay.
show you.
Oh, that is still going. Okay. I thought that was done.
Yeah. Hermitian with non-negative eigenvalues implies V dot.
Oh, you're
MV
writing the step that any V can be written as a base, decomposed along a basis. Okay.
Yeah.
That was obvious. Okay.
Yeah. So yeah, maybe it's obvious. So to do this, you'll get alpha I AI, nothing to be done here. But here, because of the orthonormality, like when I multiply it out, there'll be no cross terms. Okay, so AI prime dagger AI is one if I is equal to I prime is equal to 0 otherwise. So this whole thing evaluates to summation I, lambda I, alpha I, AI. Now the same thing, this whole thing will evaluate to summation lambda I, alpha I square, mod square. Remember the alpha is a complex, and this is when I take the dot product, I'll take the complex conjugate here, the origin alpha here. So when I multiply it, I'll get alpha square, lambda. So this is greater than or equal to 0 because the lambda is a big greater than or equal to 0. So 1 implies 2 is done. I suppose this is clear to everybody. So let's do 2 implies 1. So I mean you can almost retrace the steps. So 2 implies 1. Okay. Suppose it implies so I'll prove this statement last. Suppose this condition implies that M is Hermitian. Okay. Then I can write M in terms of my eigenbasis, like with the summation I lambda AI dagger. So just reverse. Just reverse this. Reverse the steps. Okay. So I mean, there this is easier. Like okay, so I can write M as summation I lambda AI dagger. And for every V, I know that the inner product is positive. In particular, if I take V equal to AI, this will show that lambda is greater than equal to 0. So, okay, so actually, just reverse this step. So we are done. We wanted to show 2 implies 1. We are done assuming that M is Hermitian. Now let's just see that M is Hermitian. So, so now, so V
So
and V.
take V to be the eigenvector. I'm not. Oh, we are not even assuming that M is eigendecomposable. Okay. Okay.
Yeah. So it's only singular decomposable, but not eigendecomposable. Okay. So, okay. So greater than equal to 0. So now, let's look at this. Let's take 2 different vectors X in a product My. Okay. So I know this is equal to X M dagger. Okay. M dagger is the conjugate transpose of M. And this is the adjoint property of the conjugate transpose. So this is M dagger X Y. So this I know. This is true for any matrix M. And now, so suppose X M Y is equal to X M dagger Y for all X1. So this would imply that M equal to M dagger. Right? Okay. So So now you can set up things like this. So consider so remember V M V. So this was greater than equal to 0. So this is x plus y and x plus y. So this is so without x mx plus x and y plus y mx plus y. Okay. So I know this is bigger than 0. So x dot mx is bigger than 0, y dot my is bigger than 0. In any case, I mean, what I really care about is that they're real. So what does this tell me? This tells me that x my plus y mx, okay, is a real number, okay, for all x. Okay. So what is this standing for? X my plus mx y is a real number. So the overall complex conjugate. So this is so this is x m dagger y, right? By the adjoint property part is a real number. Okay. And now, similarly, you can argue. Now take v equal to x plus square root minus 1. I mean, this is the imaginary number I. Okay, take v equal to x plus square root of minus 1. So this is where you need the complex field. Okay. And if you argue that way, so what will you get? Yeah. So if you argue that way, you we will get that x minus bar. Okay. So
You'll get that this is real, and
there's a square root minus. Yeah, this is okay. So what is this telling me? So and so what is this? Is this telling me that x and y is the same as x and dagger y? So
I guess what you want to do is you want to subtract the two, and one side will be imaginary, but the other side will
Uh,
be real, and that will create a contradiction if M is not Hermitian.
well, let's see. So okay. So X, yeah. So, okay. So what is the first what is the first part telling? The first part is telling that the imaginary parts. Okay, so this means that this imaginary part of X M Y, okay, and is equal to the imaginary part of X M dagger, right? This is what the first equation is telling me. And the second equation is telling me so that this is yeah, so the imaginary part. So so this tells me, yeah. So the real part of X M Y.
Why don't you just take X minus Y instead of X plus IY?
No, no, no. That will not put a minus sign here. This will become plus. So you can try it out. So okay. So what I'm trying to show, that if the dot product between V and MV is real, okay, then for any vector V, then N has to be Hermitian. So this statement actually does not hold over the real field. I mean, the real field Hermitian will be replaced by symmetric. So I mean, you can formulate an analog, and that will not hold. That it is possible that over real numbers you can find non-symmetric matrices such that V dot MV is always bigger than 0. Okay, but over the complex field, if you say V dot MV is always bigger than 0, the matrix has to be Hermitian. So anyway, so let me finish this. So this says that this is the real part of X M dagger 1. Okay, is this clear? So this quantity is real. So let's look at the imaginary part of this. Okay, and the imaginary part of X dot M dagger Y. So these two, the imaginary parts have to be the same. Then what will happen? The complex conjugation will negate this imaginary part, and now the imaginary part of the second number will cancel the imaginary part of the first number, leaving only the real parts added up. This is a real number. And for this guy to be real number, so let us look at the real part here. So the real part here is what it is. The complex conjugation does not change the real part. So the difference of these two real parts, if that difference was non-zero, that on multiplying by square root minus 1 would give me a non-real number. Okay. So the fact that this is a real number means that the real part of this should be equal to the real part. So what have I proved? The real parts of these two numbers are the same. The imaginary parts of these two numbers are the same. So that implies that has complex numbers x dot my is equal to x dot m diagonal. Is this clear? So this shows that m is equal to n. This is the relation. So the v dot mv being real here, I mean here we had even slightly stronger. V dot mv is real and non-negative. That condition is already enough to say that m is Hermitian. Once m is Hermitian, we can write it in the eigenbasis decomposition and then conclude that all the eigenvalues. So that is why in the literature people just say, oh, M is a positive semi-definite matrix, and that already implies Hermitian. Like they don't have to separately remind you that it's Hermitian. Is this proof clear to everybody?
Yeah.
Have you seen this, Harry?
I might have, but I don't remember.
Okay. Okay. So yeah, good. Such a refresh your
Yeah.
memory. Yeah. So yeah. So now, I mean, this part of the course will use a lot of linear algebra, especially, I mean, things around Hermitian matrices and positive semi-definite matrices. Yeah. So anyway, so I have proved finally by all these things that I proved that 1 is equivalent to 2. And the equivalence between, let us say, 2 and 3. Okay, so already 1 equivalent to 2 tells us things. So what Shanton remarked some time back, that, oh, if you have a positive semi-definite matrix, all the diagonal entries are real and non-negative. That follows immediately from the second criteria. Okay, so let me write it here. Best. Okay, so this notation I will use to say that M is positive semi-definite. Okay, so this is M positive semi-definite. Okay, this is just notation which is especially used in literature. Okay. So this implies M JJ is greater than or equal to 0 for all J. Now, why is that? I'll just take the vector to be the jth standard unit vector, which is defined to be like so 1 in the jth location and zeros everywhere. So if I take V to be the jth standard basis vector and then apply the criterion this EJ dot MEJ is greater than or equal to 0, then this criterion is nothing but MJJ, the JJth entry. So by just taking the vectors to the standard basis vectors, I get the diagonal elements, and this tells me that diagonal elements have to be real and non-negative. Okay. Can you still hear me? I don't know who the hell has signed into this. The next lecture doesn't start at this
I
time.
can hear you.
Yes,
Yeah.
I can hear.
Must be some eager person logging in for the 2 o'clock lecture, probably. Okay. Yeah. Right. So what have we learned? That positive semi-definite matrices. Okay. So they are the quantum analog of probability distributions, and so positive semi-definite matrices means they're Hermitian matrices for sure. Okay. The eigenvalues are non-negative for sure, and yeah, the additional condition was trace 1, so the eigenvalues add up to 1. But then we also saw that positive semi-definite means that the diagonal entries are non-negative. Trace 1 means the diagonal entries add up to 1. So if you want to think of classical probability as sitting inside quantum probability, there are two ways, as I said. Like you can think of the diagonal entries as probability distribution, or you can think of the eigenvalues as probability distribution. But as you'll see later, the correct interpretation is to think of the eigenvalues as the probability distribution. But in any case, I mean, if I want to embed the classical probability vector, I'll just write it as a diagonal density matrix. Then, like, the diagonal entries are the eigenvalues. Okay, so I've defined what is the basic object of study. That is the finite dimensional Hilbert spaces, and the things that we will study. It's a probability distribution of quantum states, which are defined here. positive semi-definite matrices with trace. Okay. Now, okay, so I mean, all this is mathematically nice linear algebra, but maybe a little bit of history and physics. Like, why is this the thing that we are looking at? I mean, this looks very abstract. And, yeah. So actually, this formulation comes after a lot of hindsight. I mean, it's a great intellectual achievement. So, and I mean, why should we think of complex entries and positive semi-definite matrices and all? Okay. So, I mean, a physics course would, of course, be required to do a full justice for that. But I mean, here are things, some of which may be familiar from some old physics courses. So canonical example of a two-dimensional system. So a two-dimensional quantum system means a system whose underlying vector space is C2. So it's called two-dimensional, or sometimes called two-level quantum system. So the canonical example of it, you can say, is the spin of an electron. Okay, so here is the electron. Think of it as a ball. Just a cartoon diagram. So this electron, so this is an electron. Electron has various properties, one of which is called the spin. So what is the spin? The electron has an intrinsic angular momentum. Okay. So it is as if the electron is a tiny charged ball which is rotating about an axis. Okay. And if a charged ball rotates about an axis, that creates some magnetic moment, magnetic field, magnetic moment, angular momentum. Okay. All these are related because I mean the magnetic moment is proportional to the angular moment of the electron, and the proportional factor is the charge, but we know the charge of the electron is some fixed quantity. So these are used interchangeably, like the magnetic moment or the spin. So the spin technically means the magnetic moment, but it is proportional to the intrinsic angular momentum. So this electron, you can imagine, is spinning. So this is my electron. It is spinning like this. So this is the electron. Okay. It is spinning like this, and this is called the spin. So if you're imagining it as a spinning ball, then you can talk of the axis of the spin. And this axis, okay, and you can see I've given a direction to the axis. So what is the direction given? So look at the spin, and look at the spin. Put your position at I in such a way that the spin appears to be anti-clockwise. So that's the convention. So then the ray which is coming from the electron to your eye. So that's the direction given by the arrow. Okay. So the electron is spinning somewhere. Now, if I position my eye below, the spin will appear to look clockwise. So don't position your eye here. Position your eye somewhere here so that the spin appears anti-clockwise. That is this, anti-clockwise. And then draw the ray from the electron to your eye. So that is the direction of the ray. So this is how the cartoon diagrams of electron spin are drawn. Okay. So the spin axis has a direction. Okay. And if the spin axis is entering your eye, the direction of spin will look anti-clockwise to your eye. Now this axis can point in any direction in R3. Okay, and physicists tell us that each axis gives, I mean, is a different physical quantity. Like if you want to tell, like if you want to classify all electrons by the spins, what are all the spins allowed by nature? So physicists will say that yes, like a distinct spin axis is a distinct physical system. Like in other words, what do you mean by distinct physical system? In the lab, you can design experiments which will give different outcomes for different directions of the spin axis vector. Okay. So is this part clear, Hari?
Yeah.
Yeah. So I mean, this is just how electron spins behave. I mean, you can do experiments in the lab which show that there is an intrinsic spin and intrinsic magnetic moment. So, like different axes are physically different. So this much physicists did experiments and saw the different axes are physically different. Okay. Fine. Now you may ask, okay, what are all the possible values of spin? Maybe so. It's as there are as many spins as there are a number of different axes. So okay, so because the charge of the electron is fixed, I mean essentially the speed of this spinning is fixed. Okay, so if you are thinking of it as a spinning charge ball, the speed of this spinning is fixed. That will never change under any circumstance. The only thing that can change is this axis. And of course, if you have different electric or magnetic fields in the lab, you can manipulate the spin axis. Okay? So we know the different axes are physically different, but you can ask what are all the possible physical states of the electron? Are they in one-to-one correspondence with the spins? And the answer to this surprisingly is no. They're in two-to-one correspondence with the spins. In other words, for every direction of the spin axis vector, there are two possible, so what am I trying to say? Yeah. So there are two possible electron states which correspond to that spin axis. Okay. So this is a highly non-intuitive fact, but this is actually how nature behaves. Okay, whether you like it or not. So to completely specify the physical state of the electron spin, you have to specify its axis and you have to specify one bit. So usually that bit people call it plus or minus. So they will say, oh, the electron spin is this is the spin axis. Now it is aligned parallel to it or aligned anti-parallel to it. So these are the jargon. So it's basically the set of all the physical states of the spin are in two-to-one correspondence with axis. For every axis, there are two possibilities. And this is it. This is the complete set. And in particular, so how was this detected? So experiments can be done where you have a pair of electrons and let us say, another cartoon diagram. I have some other electron here and let us say spinning like this. So let us say hold this stationary. Okay. And this I move around the other electron. Okay, you can do experiments like this. That you have a pair of electrons, some spins are there, like you can see the axis. Now you hold one of them stationary, move the other guy around. Okay, without changing the orientation of the spin axis. Now you'll think that as this electron moves around and comes back here, the physical state should be the same. But it turns out that sometimes it's not the same. Sometimes it appears that the physical state has gone some kind of what they call a flip. Like, I mean, there is an overall minus sign affecting things. And this corresponds to the fact that, as I said, for this axis, there are two possible physical states, okay, labeled by that bit, usually written as plus or minus. So it started off with the plus state along this axis, went round it, and became minus state. And well, why do you know there are only two of them? Because they again rotated it again, then that minus flips back to plus. So you can play this game. Hold this fixed, move this around. So it's as if the pluses become minus. Move it around once more, the minus will again become plus. And this is all. So as far as you can see about nature, this is all that there is still in terms.
I don't understand this at all. What's the math behind this?
Yeah, so the math behind it is, yeah, I don't want to go into it. There's very beautiful math behind it. But it is because of this, so yeah, we will, I mean, take up this example in the next lecture, that it is fruitfully modeled as a, it is basically fruitfully modeled as a, what should I say, as a 2x2 density matrix.
Okay, but I don't understand the example at all. Sorry.
Yeah, so I mean, it's very strange. So the spin is something in R3. Okay, but it is like it's as if every vector in R3 has two possible spins. So it's like what is called a two-fold cover. So again, I mean, the direction is important, not the magnitude of the axis vector, right? So so you can
I mean,
think
is
of
it like there is some, is it like the electron spin lives in some high dimensional space where you have enough space to sort of go into one
yes,
subspace and then go into another
yeah,
subspace and then come back?
yeah,
Is it
yeah.
like that?
So yeah, so the way to I mean, a little more mathematically rigorous is like, of course, the length of this vector is of no consequence, just the direction. Okay, so directions of vectors in R3 are captured by points on this unit sphere in R3. Okay, so the unit sphere, the two-dimensional unit sphere S2 sitting inside R3. So you may think that the spin states are in one-to-one correspondence in S2, but no, they're in two-to-one correspondence in S2. Okay,
Then why
so
don't we just take the sphere in C2, C3?
no, so no, then there is too much freedom. Okay, so I want to capture exactly the correct thing. So it turns out that I have to work with. Okay, so first of all, the way I defined it, it seems you don't need complex numbers at all. Okay, and it seems if anything, you have to work with three real numbers, right? Three real numbers plus one bit. But it turns out that all this is captured with two complex numbers, like three real numbers plus one bit is equal to two complex numbers, okay, with some constraints. So we'll do that next time. I mean, the length of the vector has to be unity and like the global phase doesn't matter. So those are the constraints. So yeah, so as I said, I mean, this formulation of like modeling electron spin as a vector in C2 and then like going more generally instead of vectors of 2x2 density matrices is a tremendous intellectual achievement. Okay, so all this has gone into it before, I mean, it comes out. And all this is why it is driven by experiment. So to map the experiment into a beautiful mathematical theory and then, I mean, make predictions on that. And this theory has been checked again and again and again. So it seems that this is correct. Okay, I mean, this, you may say this is, I mean, why is this the right way to model the experiments? Well, it was done and it seems to be correct because you can use the maths to predict new effects. Okay, and then experiment check for them. And I mean, bingo, like the experiment matches the theory extremely well, extremely well. So it's indeed a big intellectual achievement. It's not the achievement of one person, several persons. Okay, so we'll stop here now. Yeah. And yeah, the next lecture will take up a little bit more about the motivation, like where this 2x2 density matrix came from. And after that, I mean, we will forget the physics and we'll just work with matrices, vectors, things like that. Okay, any questions?
Yeah, I had one question. So, is it true that the one-shot in analysis is more popular in quantum world rather than the classical world?
No, not really. Oh, yeah, it is definitely more popular in the quantum world than the classical world.
Is
But
there any reason for that? Like,
no, it's just, I think, the culture of the people who've done it. But again, most of the analysis in the quantum world is still IID. Okay, the IID hangover is still there. Okay, but I mean, if you look at the one-shot people who are working, most of the one-shot people who are working also work in quantum. They may also, I mean, they may do classical stuff from time to time, but I think almost all of them do work in quantum. So, okay, let me tell you some history. So this second order analysis of the noisy point-to-point channel is just a classical. Okay, so it was first done by Hayashi, somebody called Masahito Hayashi, Japanese guy, who basically does quantum, but I mean, of course he knows classical. But he wrote it in a very strange language. It was not written in the nice language which we have developed. It was not written in terms of I mean and all. Okay, but anyway, I mean, he proved the second order rate with some strange language and all. And it was an entirely classical paper. I mean, at that point, the quantum generalization of that was actually not done by Hayashi, it was done by other people. So it was a purely classical paper, but Hayashi, I mean, probably does more quantum than classical. I mean, he's some math guy who does operator theory and quantum probability and all that. And that's his original background. But anyway, I mean, because I don't know how he thought of it, but he's the pioneer who actually thought of second order analysis. And nobody understood that. Okay? And nobody even paid attention. 1 year later, Vincent Poor and somebody independently came up with the same thing. Okay? And they are pure
Polyansky,
classical.
Poor, Verdu.
Okay, yeah. So Oliansky, Poor, and Bird. And then I think somebody remembered, oh my God, 1 year back, Hayashi did all this. Okay. And poor Hayashi's paper was not even published because nobody understood. Then, because Poor is a big name, I mean, got published, and then Hayashi's paper also got published after that, and then both of them got the Shannon Award. Okay, so
Even today, if you go to IEEE site, the Polyansky, Poor, Verdu is the most cited paper.
I think because people understand it more. Okay.
They did it
But
via
anyway.
this maximum likelihood stuff.
Yeah,
They wrote it in the language of maximum likelihood, and that got refined later into I-mean and all those things.
I mean, and all, yeah, those things came out later. I mean, there are classical roots of I-mean already before. It's just that it was never distilled out. So but yeah, so what has happened here? So how did one shot develop? So then there was this person called Renato Renner, who is a crypto guy. He does classical and quantum also, maybe more quantum than classical. He started life as a crypto guy, but then he also does a lot of information theory. So in his PhD thesis, he realized that many cryptographic constructions have a problem with composability. Like you come up with a cryptographic protocol, but if you use this protocol as a sub-protocol in something bigger, then the security guarantees go for a toss. Then he asked, I mean, what are the right kind of quantities that you should define and prove your security against so that it becomes composable? And that naturally led him to one shot. Okay. So of course, there were one-shot ideas hanging around. Long before that, there is this Khan's information spectrum, which is asymptotic non-IID, but in hindsight, it is also close to one shot. But the big motivation came from crypto then it's this community, because Renato also does a lot of quantum. They said, oh, this is a very good way to do information theory. And then people started using the one-shot quantities, which he defined, said you can do plain information theory with it, clean up things and generalize things. And then the second order analysis was understood in a much better light. New results were proved. The quantum analogs were proved. So, okay. So things got cleaned out. And yeah, so still, I think, I mean, the classical guys are not, I mean, using one shot so much, but I mean, hopefully this course will make you change your mind. That one shot cleans up your thinking a lot. I mean, it's not a panacea for sure, but it cleans up your thinking, and sometimes it allows you to prove sharper results, which you wouldn't have realized were even possible, like the second order analysis. Okay. And sometimes you do need a one shot because you are, I mean, your situation doesn't relate to the asymptotic ID, or you're doing crypto. Okay. You have finite resources and you have to do the best of what you can do. You want to extract a true secret key. You have to do the best what you can. So, yeah. But that was a general question. Any yes? If not, we will stop and meet on Tuesday.
Pranab, can you hang around for 5 minutes?
Sure, yeah. Let me stop the recording.
Yeah. Okay, so what I was saying earlier, right? So yeah, so you have